Okay, we're recording. Good. All right. So welcome to the next week here. We, at this stage, are going to go a little more deeply into the quantum chemistry or the quantum mechanics or the wave mechanics, if you want to call it that. There's a lot of different names. If you recall, we have two sort of ideas that we've looked at. The first one was this idea of energy quantization. And the way we looked at that was via the Bohr model, right? So what we said was that in an atom, you have the nucleus, and then outside of the nucleus are these levels, right? These states or orbits, whatever you want to call them, that are at specific levels. So the electron can be in one of these levels, but it can't be in between. It can only be in those specific levels. So what happens is, based on electrodynamics, if you put a charged particle at a specific distance from another charged particle, there's an energy to that, right? There's an energy of attraction. So if you're putting a limit on where the electron can be, the position, the orbit, then you're putting a limit on what the energy can be, right? So like if the energy were, or if the distance of the electron were halfway, so like halfway between 1 and 2, then you would have some energy that's different than 1 or different from 2. But what we're claiming is you can't have that. You can't have those different energy levels. You can only have the specific quantized levels, right? Which go out, in theory, they go out to infinity, but in practice, they only go up to around, I don't know, 10 or 11 or so. Okay, so that means that energy at the atomic level is quantized, with the lowest level being the ground state, right? So that's where the electron is closest to the nucleus, where the electron could be in the second level, so that's higher in energy, could be in the third level, higher in energy. And then you have this system, this series where the energy levels they converge, they become closer and closer to each other, right? Okay, so the electron can be in this level here, or it could undergo a transition to this level or this level or this level or this level, okay? So that's the first aspect of quantum mechanics, which is that energy is quantized. And quantized just means there are specific values that the electron can have or the atom can have, but not a continuous, not a continuum. So it can't have all of the possible distances, right? So if you compare that to a satellite, right? So like if you have a satellite going around the Earth, you can put the satellite into any trajectory you want, right? There's no limit to how far or what distance this is the Earth here at the center. The satellite could be anywhere. It could be, 20 miles up or 50 miles up or 50.1 miles or 50.15. You can put it in any orbit you want. All right, but you can't do that with an atom. The second issue that we came up with was this idea of matter waves. And so de Broglie had an equation, very simple equation. He said, hey, for the electron, what you have is a wavelength. It behaves like a wave, a standing wave, they call it. And you can calculate the wavelength of that electron. And it's h over mv, right? MV is called momentum. Okay, mass times velocity. So imagine the analogy would be that when we think about playing pool, right? You're playing billiards and you strike one of the cue ball with the stick. And what happens? You transfer momentum to that cue ball and it starts moving, right? So you're also transferring energy, but you're transferring what they call momentum. Momentum is a useful quantity. So then what happens is that cue ball starts moving and it hits another ball. Let's say it's the 8 ball, and it transfers momentum to that ball. right? So the cue ball loses momentum and it'll slow down once you have that collision. Most likely it's going to slow down. And then the 8-ball is going to start moving, right? So you've transferred momentum to that 8-ball, okay? So what we're claiming here is that the electron has momentum, right? It's you think of it as a particle in motion, so it has momentum, has mass, has velocity, but it also has a wavelength. So, these are seemingly inconsistent properties to say that it's a wavelength. So it's like a wave, but it's also like a particle. So what do we call that? We call that wave-particle duality, right? Wave-particle duality, that's called. And so it turns out, based on an experiment called electron diffraction, which you can use to image really small things, it turns out that at the atomic level, these particles like electrons and protons and neutrons and atoms even behave like waves. And so you actually did a problem in ALEX where they said, hey, let's change the value of H and determine whether this particle is going to behave like a quantum particle or it's going to behave like a classical particle. So there's that example of the iceberg, right? So it's kind of cool. And there's all sorts of aspects of this when you get into physics that are really amazing. There's this thing called quantum entanglement, which says that, somehow quantum particles can communicate at speeds that appear to break the speed of light, right? And so there's amazing stuff that's quite possible in terms of these properties. But we're not going to get into that. But what we are going to get into is a little bit more into it. And we're going to talk about something called the Heisenberg uncertainty principle. Okay. So the reason I'm going to spend a little bit of time on that is there is an ALEX problem, and it's called finding the minimum. So this is section 6.5. And this is called quantum mechanics. And the problem I'm going to look at is called finding the minimum uncertainty in a position or velocity. Okay, it's not necessarily a straightforward problem, and it has some terminology in it and all of that, so I want to spend a couple minutes looking at an example there. But before I actually show the example, I want to talk a little bit about this idea of uncertainty, because it's a concept that we talk a little bit about at the beginning of chemistry when we're talking about making measurements and the idea of accuracy and precision. And so generally that's covered in the previous course, Chem 100, not in this one, because I think it's in chapter 1, actually. It's either 1 or 2, so it's early on. So we didn't really cover that in this course. So let's talk a little bit about it. Let's talk about this idea of uncertainty. Uncertainty has to do with the idea that you're uncertain about something, right? So for example, imagine that you're going to walk into a room, but the door is closed, right? And so you're outside the door. Here's the door, you're outside, and there's people in there, right? And they're all talking. Now, because of the wave properties of sound, right? Sound is a wave. You might be able to estimate how many people are in that room just by listening to the sounds coming through the walls, right? For example, if there was only 2 people in there talking, that would sound a lot different than if there were 20 people in a party talking loudly. You would be able to make some sort of estimate, but you recognize that you might be able to tell if there's 2 or 3, but you probably couldn't tell whether there's 19 or 20, right? That difference would be more difficult to determine. So what you're doing is you're doing an estimate, right? And what we would claim is that there's some uncertainty in your estimate. So you might say, hey, I really don't know. There might be 10 people in there, but there could be 20. I know there's probably not 30 because the room's not big enough for 30 people. And listening to it, I know it's more than 5, but you might say it's between 10 and 20, right? And that's a range, right? That's a range of your estimate. And we can call that uncertainty. And so we might report it like this. We might say that there's 15 people in there plus or minus 5, right? Does that make sense? Meaning that it could be anywhere from 15 minus 5, which is 10, all the way up to 15 plus 5, which would be 20. So anywhere from 10 to 20. But again, we may not even be that sure of things, right? We might say, look, there could be as little as 5 in there, and there could be as many as 25 in there. I just really don't know based on the sounds. So in that case, you might say, okay, there's 15 plus or minus 10, right? How did I get that 15? What I did was I said, what's the midpoint between 5 and 25? What's halfway between the minimum and the maximum? You know, and so that would be 15. So 15, and then, you know, it could be as little as 5. So 15 minus 10 is 5, and it could be as big as 25. So 15 plus 10 is 25. And what we would claim is that this has a greater uncertainty, right? And this one here has a lower uncertainty. All right, an uncertainty of 5, right? That's not too bad. An uncertainty of 10 is not as good. Now, you can also do it as a percentage, right? So what you could do is you could say, hey, you know, 5 is what percentage of 15? Well, 5 over 15 is a third. Convert that to a percentage, you multiply by 100, so you get about 33%. So we could also write the uncertainty as 15 plus or minus 33%. And then for the second one, well, 10 is 2/3, right? 10 over 15 is 2/3. That's 67%. So for the second one, it would be 15 plus or minus 67%, approximately. It's 2/3, right? So again, you have a greater uncertainty here. So notice how that's done as a percentage instead of as a raw number, right? As an absolute number, an absolute value there. So this is actually the way you're going to see it for these problems. They're going to give you the uncertainty as a percentage. Okay, so that's a little bit of discussion, just a real intro. I'm no expert on uncertainty measurements, but that's our sort of intro into that idea. The second thing I want to talk about is what's called the Heisenberg uncertainty principle. And this is a fundamental concept in measurements, whenever we make measurements. Most of the time, we don't have to worry about it. So if you're measuring a cup of flour, you don't have to worry about the Heisenberg uncertainty principle. If you're measuring a gallon of gasoline, you don't have to worry about the Heisenberg uncertainty principle. If you're measuring your weight on a scale, 140 pounds, you don't have to worry about the Heisenberg uncertainty principle. But it turns out that if you're measuring anything that involves atoms, an individual atom or an individual electron, the Heisenberg uncertainty principle suddenly becomes important in terms of your measurements. And let me show you one kind of analogy to think about that. So what I'm going to do is I'm going to imagine that you have, I guess it's easier for me to draw a bicycle. So imagine you got a bicycle. Right? And this bicycle is moving. And let's say its velocity or its speed is 15 miles per hour. Okay, that's how fast it's moving. And suppose you want to measure how fast it's moving. Well, one way that you could do that is, let's assume you don't have any high technology, right? You don't have a laser gun or something like that. So what you could do is you could say, hey, I'm going to put a little piece of tape on the ground here, and I'm going to put a 0 next to that tape. And then I'm going to measure, you know, 100 meters. So I have some measuring tape I can measure off 100 meters, right? Okay, so that's a distance, right? So there's 100 meters. And then what I could do is I could stand right here and measure with a stopwatch, right? And I can measure how long it takes for this bicycle to go 100 meters. And so then I would get an average velocity, which would be the distance, 100 meters, divided by the time, which let's say it's, I don't know, let's make it 5 seconds. And you would get a speed that's 20 meters per second. That'd be an average speed, right? So let's not worry about it going 15 miles per hour. Okay, and there you go. So you've now measured how fast on average that bicycle's going. It might have changed, it might have gone faster at the beginning, but on average it's going 20 meters per second. That's actually pretty fast. That's actually around 45 miles an hour, but whatever. Say it downhill. So now, how did we make that measurement? What we did was we stood here and we used light, right, from the sun. It's kind of interesting, right? The sun is shining light. And so light is constantly streaming down on the surface. You can't do it at nighttime, right? Like if it's dark outside, this experiment doesn't work. You might be able to do it from moonlight, but you know, you would say, well, it's probably not going to be quite as good of an experiment. Some of that light reflects off of the bicycle and goes right into your eyeball, bounces around in your eyeball. It's then absorbed by a molecule called rhodopsin, and the rhodopsin molecule undergoes a little conformational change, and then that sends a chemical signal that's perceived in your brain, right? So the whole time, I mean, you really only need 2 measurements. You need it right here. When is the bicycle crossing the 0 mark? And then you need it again here, right? So the bicycle at some point is over here, and then that's going to bounce off into the light's going to bounce off into your eye. And now you've made those 2 measurements. In both of those measurements, you had to use light, right? So we're using light to make that measurement. And that's true essentially with atoms as well. Now there's some exotic experiments you can do, but they all essentially involve the same thing, which is if I have an atom, and let's say that I want to know something about the electron. Okay, so we know an atom has electrons. Let's make it simple. Let's just worry about 1 electron, which is in this atom. And I tell myself, I want to know where that electron is in the atom because, you know, as humans, we want to know what things are made of and we want to know what their structure is. You sometimes see little cartoons where people will zoom in with a microscope and show that, you know, at the atomic level, there's actually a whole nother universe with people and stuff like that, right? Turns out it's not true. It can't be true. And there's a reason why. It has to do with how differently nature behaves at the submolecular or the subatomic level than it behaves on a larger scale, right? On a larger scale, which is our scale, the universe actually behaves quite differently than it behaves at the atomic level, okay? Very differently. So let's talk a little bit about this idea. Let's say that what I want to do in this atom, and you can actually measure the size of an atom. Atoms are, you know, roughly speaking, approximately 10 to the minus 10 meters in size, okay, which is called an angstrom. It's an outdated unit. We don't use it that often, but you'll sometimes see it in, there's a symbol. You'll sometimes see it in textbooks. It's called the angstrom. We use the SI system, so we use like powers of 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, micro, nano, pico, but this, you know, the angstrom is kind of cool. And it's useful because that's essentially the size of an atom, right? So how do you tell? Oops, I almost left the meeting. How do you tell the size of an atom? Well, we're not going to go through it in this course. Unfortunately, we don't have time. But it turns out that atoms are stacked right next to each other in solids. So they're like this, right? They're like oranges in the grocery store. So they stack like this in solids, particularly in things like salt, okay? Or metals. Metals is a good example. If you have a piece of aluminum, the aluminum atoms are just stacked right next to each other like this. So really all you got to do is then you just got to say, hey, how far apart is the center of one atom from the center of the next atom next to it, right? And that distance between those two centers is actually, you know, if you look at it geometrically, that distance right there is the radius of one of the atoms plus the radius of the other atoms. So if those are the same atoms, that those two radii together is actually the size of the diameter, right? Because two radii equal one diameter. So you're actually measuring the size of the atom. And you can do that with X-rays. There's some other ways you can do it, some exotic ways as well. You can bounce a little piece of metal across the surface and it will deflect light back and forth, and you can measure the distance that way. But the traditional way is through what's called X-ray diffraction. So you can measure the size of an atom. So if we can measure the size of an atom, and that works pretty well, we can know it really well actually, then maybe we can figure out the internal structure of the atom. Where is the electron? What's it doing? Is it moving like this? Is it moving like that? Does it change directions? And then we have this issue, well, wait a minute, we said it's a wave, so it's actually spread out across the atom. So let's think a little bit about this. If you want to know where something is, what do? You focus the light onto a smaller and smaller spot. So those of you that are biology majors, you recognize that, you know, if you've got a cell, what can you do? You can actually image the cell by putting a stain in it so that this molecule that absorbs light will absorb to certain molecules like proteins or DNA, that kind of stuff. And then what do? You shine light, right? And you shine light on this cell, the light bounces off, you know, and that gives you an image of it. And if you want to know even more, you know, you really want to know the internal structure of the cell, what do? You focus the light more, right? Like you use either a mirror or a lens to focus the light onto a smaller and smaller section, right? And then you can look at, oh, I'm just going to look at this organelle that's in this cell, right? And that works pretty well up to a point, right? So let's say we want to do the same thing with this atom. We want to know where the electron is. So now we're going much more deeper. We're going into one atom in that organelle. So what you want to do then is a couple of things. You focus it more, right? You got to focus it into a more narrow and narrow beam. But it turns out there's a limit to how much you can focus light. The limit is essentially that light has a wavelength, right? So you can't focus the light to any smaller distance than the actual wavelength of the light. And the wavelength of the light for visible light is 400 to 700 nanometers, right? That takes us back to the beginning of the course, Roy G. Biv, right? Red is over around 700 and violet is over at 400. So you say, okay, well, what happens? Okay, so we can't use visible light because it turns out this is actually bigger than molecules even. 400 to 700 nanometers is actually bigger than a molecule. So you can't use visible light to look at molecules. There's some tricks you can do to kind of get a little bit better. But for the most part, you can't use that. So what do? You say, well, let's get smaller and smaller waves. So the next thing is ultraviolet. So ultraviolet goes, you know, anywhere from 1 nanometer up to 390 nanometers or so, right? Almost 400. That's pretty small, 1 nanometer. Now, 1 nanometer is actually the size of a molecule, of a relatively small molecule. So you're getting closer. But again, you know, 1 atom is even smaller than that. So what do? You say, okay, now we got to go to X-rays. So now you say, you know, we're going to go from, you know, 10 to the minus 2 nanometers up to a nanometer or so, right? So now you're starting to get there. You're starting to get to the size, the wavelength of an electromagnetic wave that is getting close to pretty much the size of the atom and even a little smaller than the atom. So now you might be able to use X-rays to image, right? So instead of sending invisible light, you're going to send X-rays in there to image the atom itself, 1 atom. That'd be so cool. You could actually see what the structure of an atom is, which is something people have wondered about for thousands of years. And here's what the Heisenberg uncertainty principle says. It turns out you can't do this. And here's the reason you can't do it. We have this little relationship that we looked at earlier. So if you're talking about photons, you're talking about electromagnetic waves, right? the energy of a photon is equal to h times the frequency, right? But then in terms of wavelength, it's h times c divided by wavelength. And here's what happens. Every time you make this shorter, right? What we're doing here is we're changing it to shorter and shorter wavelengths. This is a smaller number than this is, so it's a shorter wavelength. Every time that gets shorter, this one gets larger, right? Think about it mathematically. If you make this number in the denominator larger, that's going to make the ratio smaller, right? But if you make this smaller, shorter, that's going to make this larger over here on the left side. So here's what ends up happening. You send in this photon, which has a really short wavelength, and it hits the atom. It turns out that that photon has so much energy, it will actually knock the electron right off of the atom. So you can't even tell where that electron is in the atom because the photon actually knocks it out of the atom completely. And now you've lost all information about where that electron is. That is the sad or a sad aspect of this relationship, this sort of inverse relationship, that you can't see the structure of the atom with visible light because visible light's too big. It's sort of like, you know, painting, you want to paint something really, really small, but you have a gigantic roller that you use for your wall. You can't paint something really tiny with a big roller, right? Same thing here. You can't see the internal structure of an atom with something that has a gigantic wavelength. You need a really tiny wavelength. But unfortunately, as that wavelength gets smaller and smaller and smaller, the energy becomes so large that it knocks the electron off completely. And so you're lost. You don't have a solution to that problem, and we're just sort of stuck with that. So the relationship that we're looking at here is the relationship between velocity and position. It turns out because, you know, velocity is related to energy, right? Kinetic energy is 1/2 mv squared, right? Velocity and position cannot be known perfectly. You can know one of them better. So it turns out with the electron, if you use these X-rays, you can figure out the velocity of the electron in the atom, but you lose information about its position, and vice versa. You can know the position of the electron in the atom, but you lose information about the velocity. So what that means is we can't tell what the electron's doing. We have no idea what it's doing, so we have to give up that information. So velocity and position, and we're going to look at that example in a moment. It turns out there's some others as well. The most, perhaps the second most famous is energy and time. We're not going to look at it in this course. It's a fascinating relationship. It turns out if you want to measure energy at the quantum level, you lose information about time. You can't know both of them very well. And it turns out this gives us some insight into the universe. If you take a perfect vacuum, let's say we go way out into outer space, in between galaxies, see space in between galaxies where there's nothing in there. And you take a little volume of space and you say, hey, there's completely nothing in there. So how much energy does it have? Shouldn't have any, right? There shouldn't be any. If it's completely empty, there shouldn't be any energy. But if you measure it over a period of time, so if I make this large, what that does is it means that this becomes a specific value. It's a small value, right? So if this is large, this one's small, but it becomes a specific value. So it turns out, even if it's empty, there is energy in that space. So space itself, even if it's in a vacuum, it has energy, okay? So those are the two relationships. We're not going to deal with this one. We're going to deal with this one right here. And so I'm going to write the equation out for this one. And then I'll talk about the equation. It's delta P times delta X is equal to h over, gosh, I want to make sure I think it's 2 pi. It's either 2 pi or 4 pi. I'm sorry, let me make sure. Sometimes it's 4 pi. I'm sorry. And actually, I'm going to, instead of saying equal sign, I'm going to say greater than or equal to. There we go. Okay. So this is often referred to as the Heisenberg uncertainty equation or relationship. Relation, I'll just call it relation. And I want to talk a little bit about it before we look at the problem because it's not obvious. So delta P is the uncertainty in momentum. And momentum is mv. And so delta P is really, mathematically, it's m times delta v. So this is the uncertainty in position. I'm sorry, velocity. The mass is not an issue. We know what the mass is of an electron. It's the velocity that we have uncertainty in. So what this says is delta P is the mass of the electron times the uncertainty in its speed, meaning is it going 100 miles an hour or is it going 100 miles an hour plus or minus 50 miles per hour? Okay, remember the uncertainty is plus or minus, okay? So that's the uncertainty in the momentum. So mass we know, so there's no uncertainty in that. Then it's times delta x, which is the uncertainty in position. Okay, where it is. What we're claiming is that if you multiply those two together, the smallest that product can be, the smallest it can be is h over 4 pi. That's the smallest possible value. But it can also be greater than that. But we're not going to worry about greater than, we're just going to worry about equal to. So for the problem that you're solving where they ask you to find the minimum uncertainty, you just set it as equal sign. And so in all practical purposes, the calculation is it's an equal sign, okay? But it could be larger than that. So what that says is, if you want to know how fast it's moving, so what's its velocity, this is the electron again, and you want to know where it is, right? So where is it on the x coordinate? How fast is it moving? There's a minimum value it can be, and that minimum value is h over 4 pi, okay? Which is just going to be a number. H over 4 pi is the h that we've used over 4 pi, okay? So let's look at a problem. Escape there. So the issue here is they say, hey, you've got this atom of argon. And it has a radius of 71 picometers. Okay, like I said, we can measure the size of an atom pretty well. The average speed of the electron in it, of course, there's more than one electron, but they're saying the average of all the electrons is about 3.9 times 10 to the 7 meters per second. Calculate the least possible uncertainty in the speed of the electron. In the atom. Okay. Answer it as a percentage of the average speed. Okay, so that's the problem right there. Okay. Oops, there we go. All right, so let me show you a little drawing here of what we're claiming. So you've got this atom. Okay, They're giving you the radius. So there's your radius, and the radius is 71 picometers. Now what they're claiming is there's an electron in this atom. So don't worry about, argon has 18 electrons, but they're just saying the average of all those 18 electrons is this value. So just on average, okay? We're talking about the electron, right? So the electron, all right, that's the particle we're interested in. The radius is 71 picometers. And what they're saying is the speed, the velocity is 3.9 times 10 to the 7 meters per second, which is actually really fast. 3.0 times 10 to the 8th meters per second is the speed of light, right? And that's the highest speed you can get. So this is around more than 10%. It's more than 10% the speed of light. So that's really fast. Electrons are moving very quickly. So calculate the least possible uncertainty in the speed. So uncertainty in speed, that's the key there. We want uncertainty in speed. So what I'm going to do is I'm going to write the equation here. Delta P times delta X, and I'm just going to use equal, even though it's greater than or equal to, we're finding the minimum uncertainty. So we'll just set it as equal to H over 4 pi. Okay. And then they say they want the uncertainty in the speed. So that's over here, delta P. So what is delta P? Delta P is M delta V. So M delta V delta X is equal to H over 4 pi, right? Mass of the electron, not the, we want to know the uncertainty in the speed of the electron, okay? So the electron is the particle we're interested in. So the mass of the electron, the uncertainty in the speed of the electron times the uncertainty in the position. So what they do is they essentially say the uncertainty in the position is the size of the atom. So I'm going to write delta X is going to be the size of the atom. Right? So we're assuming the electron's in the atom, right? So what would that be? Well, the size is not the same as the radius. The radius is half the size. The size is 2r. Diameter equals 2r, right? So this would be 2 times 71 picometers. So that's 142 picometers. So there's your size. That's what we're claiming is the electron's somewhere in that region. Now we want to know how fast it would be moving, what the uncertainty and the speed would be. Okay. So what's the mass of the electron? That's easy. That you just look up. It's 9.109 times 10 to the minus 31 kilograms. Make sure you use MKS system for these problems. Do not use CGS. Don't use centimeter, grams. Use kilograms and meters. Okay. So essentially, here's what happens. We know that number right there. We got the mass. That's just a constant. We've got this number. That's the size of the atom. This is a constant. We know what that number is. And 4 pi is a constant too. So we know everything except delta V. And that's what they're asking us for. So delta V would just be H over 4 pi. And then I'm going to divide both sides by M. And I'm going to divide both sides by delta X. And there you go. H over 4 pi M delta X. That would be your uncertainty in the velocity. Remember, delta V is the uncertainty in velocity. Delta X is the uncertainty in position. If they told you the uncertainty in the velocity and then they wanted to know what the uncertainty in the position was, you would just do it the alternative way, right? You would put delta V on the right side and you would have delta X on the left side. Those are the only real two options you can do. Okay. So now it's just a matter of getting everything in there with the correct units. And you might get confused about H in terms of the units because H is in joule seconds, but mass is in kilograms. So I'm going to go through the whole dimensional analysis nonsense here. Let's go through it. Delta V is H. So that's 6.626 times 10 to the minus 34 joules times seconds. But remember, a joule is a kilogram meter squared per second squared. So if you have joules times seconds, you're going to get kilogram meters squared per second squared times seconds. So one of the seconds down here is going to cancel with that one. So I'm just going to write it as kilogram meters squared per second, right? Because one of the seconds cancels because the H is joules times seconds. So there's your H. Everything else is in the denominator. So I hope I have enough room here. 4 times pi, so that's 3.1415. And then you got mass. Now here's our mass. 9.109 times 10 to the minus 31 kilograms. And then delta X. Just be careful. Delta X is the size of the atom. It's in picometers though. And we want to have it in the MKS system, which is just meters. So what do? You just say, hey, 142 picometers is 142. Pico's 10 to the minus 12. So 142 times 10 to the minus 12 meters. Okay, so what happens? Some units cancel. Kilograms, 4 pi has no units. You got a meter here, you get rid of a meter there, so you got meters per second. So it's just going to be delta V is going to be in meters per second. Okay, so let me just run through the actual calculation. Okay, let's see. So it's H over 4 pi m delta X. So let me see if I can do that on my little calculator here. Okay, unfortunately, I have to switch this over. Okay, so 6.626. Oh, shoot. All right, that's not going to work. Terrible calculator. Let me come back over here. I'll just do it on my computer. Okay, 6.626 times 10 to the minus 34 divided by 4 divided by pi divided by 9.109 times 10 to the minus 31. And then we're going to divide it by 142 times 10 to the minus 12. Okay, so here's what we get. 407,645 units or meters per second, right? Okay. And I'm going to go ahead and put that into scientific notation. So I'm going to move this 1, 2, 3, 4, 5. So 4.076 times 10 to the 5 meters per second. So there's your uncertainty in the velocity. Okay, so H over 4 pi m delta X. That will give you the uncertainty in the velocity. Now, the only thing that's left is they just want you to say, look, put your answer as a percentage of the average speed, right? So what does that mean? Let me erase some of this over here. Okay, as a percentage, really what they're saying is, what is delta V over V times 100%, okay? That's what they mean. They're saying as a percentage of. When we say something is as a percentage of, what you're saying is it's out of compared to something else. So the ratio of this divided by that. So if I said, you know, you have, you know, 10 blue-eyed people and 90 brown-eyed people. What is the number of blue-eyed people as a percentage of the total? you would say 10 over 100, because there's 100 people total, times 100, and that'd be 10%. Same thing here. So it'd be delta V, which is 4.076 times 10 to the 5 meters per second, divided by the average speed, which was 3.9 times 7. So that's where that number comes into play, right? You don't use it until you get this. And then times 100%. Okay? And, you know, you can play a little, actually, it's kind of an interesting problem. They made the numbers work out pretty nicely. So what happens is this. If you take 10 to the 5th and you multiply it by 100, that becomes 10 to the 7th, right? 100 times, 100 is 10 to the 2. So 10 to the 2 times 10 to the 5th is 10 to the 7th. So that 10 to the 7th that you get there is going to cancel with that 10 to the 7th there. So you just end up with a nice little calculation. So they made these numbers work out on purpose. They picked a speed such that it would give us this. Okay, that's pretty good. So it looks like it's a little more than 1%. So 4.076 divided by 3.9, and it looks like you get about 1%, 1.0%. Okay. So that's actually not bad. You know, that's pretty good. What they're saying is the minimum uncertainty that you can get in this experiment is about 1%. That's actually not so bad, right? The reason it's not so bad is because they made, you know, the size of the atom is pretty large. So the uncertainty in the position is pretty large. So you can measure, you know, how fast something is moving to about 1%. That's not too bad. But you have essentially the electrons anywhere in here, right? So you really don't know where the electron is in the atom. You're just saying, hey, it's in the atom. So the uncertainty of the position is really large. That's your delta X. If this is really large, this one can be small. 1% is not that bad, okay? So to know the uncertainty and the velocity even better, we would have to make the size even larger. So the electron could actually be, you know, even larger. But as you narrow down the size, the uncertainty in the velocity gets bigger. So that's kind of a cool problem. So for these, I think there's really only two types of problems they show you. The first one is they give you the size of the atom, and then they ask you for the uncertainty in the, you know, in the, they give you the velocity, they ask you for the uncertainty in the velocity. And then the other one is they give you the uncertainty as a percentage, and then they ask you for the uncertainty in the position. So let me just, I'm not going to go through the whole problem, but I want to show you one more example, just kind of help you get started on it. Suppose they say you've got an atom of xenon, and they give you the radius, just like we did before, right? And here it's 108 picometers. Okay. And then they tell you the average speed is 137 meters per second. Okay. So there, same thing. They're giving you the speed. Now this is a lot smaller. So now they say they measure the speed. So they measure the speed to 0.010%. This is your uncertainty, right? That right there is uncertainty. Okay. And then they say calculate the smallest possible length of a box inside which the atom could be known. Okay, so let me go through the, I'm just going to set this up for you. You can do the actual calculation. The numbers aren't that bad. But essentially what we're saying is, look, imagine you put this atom in a box. And let's say the atom is this big. It fits perfectly in the box like that, right? And the radius is 108. So what's the size, right? The size would be 2r. So that would be 216 picometers, right? That would be the size of the atom. So that's what they're claiming for this xenon, is that it's 216 picometers in size, right? Diameter equals the size, which equals 2R, which equals 2 times 108 picometers. Okay, that's where that number comes from. Now what they're saying is that the average speed of the electron, the average speed of the atom. So this is the average speed of the atom. Okay, so this is a little bit different than the one we just did. The previous one was the electron. Now we're talking about the speed of the atom. That's why it's going so much slower. Okay, so now here's what we got. Delta P times delta X. Again, just use equals h over 4 pi. Okay, 4 pi. Now, this is the mass times delta V times delta X is equal to h over 4 pi. Okay, that we did before. Now, you're going to use the mass of the xenon, not the electron. So now we're talking about an atom that's moving, right? So in this problem, they say it's a gas. So the atom itself is moving, not the electron, but the atom itself. Okay. All right, that's fine. So what's the mass of a xenon atom? You look it up in the periodic table, and then you do a little conversion, okay? So let's do that, actually. I'm going to look up the atomic mass of xenon. 131, so it's 131.29 grams per mole, right? Or one atom is 131.29 AMU, right? That's one atom. Remember, this is a mole of atoms. That's in grams. So this is 131. But unfortunately, AMU is not an MKS unit. It's an old unit, right? So how do we deal with that? We just do the conversion. The conversion is 1 AMU is 1.661 times 10 to the minus 27 kilograms. That will allow you to convert AMU to kilograms, okay? Taking up a lot of space over here, but that's essentially what you do. So you got 131.29 AMU, and then you want to just put 1.661 times 10 to the minus 27 kilograms per AMU. And the reason you need that, that's going to give you kilograms, is that you need to know the mass of the xenon atom in kilograms, right? Just like we did with the electron in the previous problem. So that's going to give you that problem, right? That value right there. So you now know the mass of the xenon atom. We also know H and we know 4 pi. Those are just constants. So what else do we know? What they say here is the uncertainty in the speed. That's the uncertainty in the speed, 0.01%. That's delta V. They're giving you delta V information there. Okay? So now you say, okay, if you have delta V, you would have this, right? But the problem is it's done as a percentage. It's not done as an actual value of 10 meters per second. It's done as a percentage of this. And that's the tricky part for this problem. They're giving you the speed, so there's your V, and then they're giving you delta V as a percentage of V. So I want to show you how to do that part. It's not an obvious issue. So what they're saying is that 0.010% is equal to delta V over V times 100. Remember, it's a percentage, so that means it's times 100. So here's what you do. You just say 0.010 is equal to delta V over V. Divide both sides by 100. Right? Because if you divide the right side by 100, that gets rid of the 100 on the right side, and now you just have delta V over V. So you get 0.01 over 100, so that's that small number. That's 10 to the minus 4, right? 0.01 is 10 to the minus 2. Divide that by 100, you get 10 to the minus 4. That's equal to delta V over V. So you want to know delta V. We're trying to find the uncertainty. So multiply both sides by V. And there you go. All right. So what is V? 137. So 10 to the minus 4 times 137 meters per second is 137 times 10 to the minus 4, which is 1.37 times 10 to the minus 2 meters per second. So there's your uncertainty, right? So that's a little tricky there. They're giving it as a percentage, so you have to understand what that percentage means. So now we've got our delta V, okay? 1.37 times 10 to the minus 2 meters per second. So you got your mass of the xenon atom. That was done here. You got to convert AMU to kilograms. You've got your delta V starting with the percentage, but actually getting to a meters per second. And then now you can calculate delta X. That's what they're asking for you. So same thing, you just divide both sides by M delta X, and then you still have your 4 pi right there. 4 pi, sorry. I didn't write that very well. 4 pi, okay? So H over M delta X, M delta V, sorry, M delta V times 4 pi, and that'll give you your delta X, okay? Now let me just check real quick, because sometimes they ask you to give the answer in slightly strange units. Yes, so in this particular one, they ask you to give your answer in atomic radii. So here's what's going to happen. So you're going to end up with a delta X. So let's say, I'm going to come up with a value. Let's say delta X, I'm just making this number up. This is not based on the numbers we just had. Suppose that, okay, 108. Suppose it's 5.2 times 10 to the minus 11 meters. So you end up with that value. And then again, the size of the atom was 216 picometers, and the radius of the atom was half of that, 108 picometers, okay? So suppose you get delta X is this, and then the radius is 108 picometers. They want you to give the answer in atomic radii. So what they mean by that, they kind of explain it a little bit, but what they mean is, you know, one radius is 108 picometers. So convert your delta X to picometers. Okay, so I'm going to do that. 5.2 times 10 to the minus 11 meters. And then a picometer is 10 to the minus 12 meters. Okay, so if you do this, here's what you end up with. You end up with 52 picometers. Okay, so 5.2 times 10 to the minus 11 divided by 10 to the minus 12 is 52 picometers. So there's your units. The meters cancel. So now you say, okay, here's the radius, 108, right? So now you write it this way. You say 52 picometers divided by the atomic radius. Okay, and so that is going to be equal to, I'm just roughly estimating, it's around 0.5. So you would write this as 0.5 R. You know, it's half of a radius, right? One radius is 108. You got 0.5 divided by 108, so it's half a radius. So really what they're saying is the uncertainty is about half the size of the radius of the atom, okay? So that particular problem, mostly what you're going to struggle with are just getting, you know, reporting the numbers in the way that they want you to report them, okay? So those are essentially the two ways they represent the problems. The first one's the easier one. The one I just did right there is a little bit harder, but you can watch this video as many times as you want and kind of run through it, and you should be okay with that, okay? Now that took a long time. I spent essentially an hour on that problem, but that problem is pretty tough. It's pretty demanding in terms of unit analysis and then also the theory of it. So on Wednesday, which is tomorrow, we'll get into quantum numbers, which is a little bit less intense mathematically. So we'll do a quantum numbers, which is 6.6 tomorrow. And we may actually, let me take a look. 6.7 is really not that much either. So we might be able to do 6.7 tomorrow as well. And then Thursday, we'll do electron configurations, which is kind of fun. The last section is pretty easy, but that will lead us into chemical bonding. So we may be able to wrap up on Thursday. If not, certainly the first day of next week, we'll finish that up. Okay. Good. Cool. All right. Let's see. I don't think I have any announcements. Oh, I should make an announcement. I graded I think it's the third experiment, right? It was the acetic acid, the titration experiment. So that's been graded. So check your scores on Alex. It should appear as determination of acetic acid in vinegar. That's the experiment. So that should be up. And some people are still taking the exam, the most recent exam. So those will not get graded until the final day that people are allowed to take them, which I forget is, I think this is coming weekend. Okay. So reach out to me if you have any questions, and good luck. Have a great week, and I'll see you tomorrow.
Thank you.